evaluating the limit, the big thing here is, do you guys remember the notation? When we have this little minus right here, that's called the left-hand limit, so we're going to seek out -6. So this is the point of interest. And then we're going to look at the left side of the graph and which way is, or what is it approaching. So if I follow up the numbers that are less than, or I should say numbers that are to the left of 6, that's -8, -7, -6.5, -6.1. All of those are approaching the output of 4. Now remember, the limit isn't what's happening at exactly the point, it's as we approach that. So you should have got +4 for the limit as x goes to -6 from the left. And then if we look at it from the right here, we're still looking at -6. But now we have what's called the right-handed limit. So I want to pick numbers that are to the right of 6. Those are numbers like -4, -5, but we want to get as close as possible to -6. So we're going to follow the graph up and see where is that approaching. And again, it's not what's happening at the point. It's what numbers are we approaching as we get close and close and close to 6 from the right. So think of numbers like -5.9, -5.999. All of those would have outputs that are close to 7. Now, we have the right-handed, the left-handed limit. When there isn't a marking and it's just the -6, we call this the two-sided or two-handed limit. And the only way that exists is if the left and the right are equal. If the branches of the graph were fingers, they'd have to touch, right? And in this case, they don't. So in this case, this title does not exist. All right, and then we always throw this in here. This goes back to Algebra 1. Notice there isn't the word limit. It's just the point, which is the location. This is saying when x is -6, what is the output? And in this case, there isn't any filled-in circle at -6. So this is either undefined, you could write undefined, or you could just say it does not exist. Right? If there's a filled-in circle at one of those spots, then we would know where the location is, but in this case there's not. All right. I want to show you just quick, because we're getting closer to the end of the year, and it's always a good reminder for you guys to just kind of see what is going on. Get rid of that. So we are currently, what is it, the 13th? Today we're doing the one-sided limits with tables and graphs again, but we're going to make a stronger connection to what happens now when x goes to positive or negative infinity. And we're going to make a kind of a connection to what we'll be doing next week as well. So all of this builds on each other. Quiz on Friday, make sure you do that. And then we have one more week of learning new material. That's the 17th. And then we'll have a quiz on that Friday. And then we have a review. And our final for this class is actually going to be on the 27th, Thursday the 27th, because senior's last day is that Friday. So that way we're all done, and that leaves us with the next week. Any juniors that are in class, we'll just have a quick little touch base, get attendance, here's a survey, and you're done. So not a lot left. The last day to turn in any late work is going to be the day of the final. And my goal, hopefully, is you get all that work in before you take the final, and then I can grade that night. And seniors, your job on Friday will be to look at your grade and see are there any errors? Did I miss a quiz that you took? Or was there something that we need to talk about? Because then I'm going to finalize seniors' grades at this point. Basically, I'll do juniors as well, but juniors will have an extra day to talk about it. So, all right. Hopefully that's on your radar, especially if some of you guys are missing tests, quizzes, or you're planning on doing a remediation of some type. So today is officially 12-1 day 2. Same idea as Monday, Tuesday. Limits of a function, if they exist, as we saw in the warm-up, they don't always have to exist. But now let's really look at them more from a table side. And what about specifically going to a specific value? How do you guys feel? I'm debating on whether or not we want to do all of these. How do we feel on this right now overall? Like, pretty decent? Okay. Then I don't think we need to do all of these. I actually want to do one that's a little unique. And it hasn't come up. So what I'd like you to do, you don't have to write this down. But I want you to see if you can answer these questions with a 9 plugged in there. And let me see if I can make this graph a little bigger. Oh, that's not cool. There we go. All right, so let's take a look at this. This little negative here stands for the left, so it says as I approach 9 from the left, so that's numbers that are just less than 9, so like 8.9, 8.99, 8.9999, where are they headed? We're headed close to the output of 4. Nothing special there, right? But what about this one? It says tell me to evaluate from the right-hand side. So I want to look at the numbers of f of x as x approaches 9 from the right. So those are numbers just greater than that. Well, I have a problem. I don't have the right side of the graph, and that will happen. Which means this doesn't exist because there isn't a branch of the right side of the graph. So I do want you to know that that is an option. And in that case, the left and the right-hand side are not equal, so the two-handed limit, the one without that special notation, can't exist because there's only the left-handed limit to evaluate. However, does the point exist? That's a filled-in dot right here, and that dot has an output of 4. Remember, another way to think of points in this notation is when x is 9, y is 4. Those are equivalent. So I just wanted to show you that because we didn't talk about the fact that, you know what? If your graph ends and there's nothing else on the right-hand side, then the right-handed limit can't exist and neither can the two-handed limit. So, okay. So we don't have a ton today because we're really going to look at, okay, now what if I give you a function and we're only going to evaluate this function as x goes to negative infinity. And this usually is just conceptually something that students struggle with. So we're going to look at it in 3 different ways. What does it look like with a table? What does it look like if I just plug in substitution? And these are kind of the same thing. And then we'll quickly just throw this in Desmos and look at a graph. So I'll give you a second to just write this top part. So, they want us to pick a table, right? Let's make a table as x approaches negative infinity. Now, right away, we know that negative infinity is a number we can never reach. It's a concept. However, we can try some things that are really going to help us out. And I know you wouldn't do all this, but what if we said, what's the value as x goes to negative 100? Because that's getting us a little bit closer to negative infinity. So if I plugged in negative 100, what would my output be? Now, we're not going to go super crazy. I'm not going to reduce fractions. But we know we get negative 300 minus 2. So negative 302 on top. Now, what if I at the bottom, I get negative 600 plus 12. So I get negative 588, right? And then what would happen? We get the negative divided by negative. That ends up being a positive number. I might even write that one down. So throw my calculator. So I get 0.5 roughly, right? 0.513. So that's not really that close. So what if I pick a larger number? And again, I'm not going to write all this out. I'm going to just quickly throw out my calculator just to see what's going on. I get 0.5013. And you can see this is pretty tedious, right? You don't want to keep doing it. But the question is, where is this going to go? And this is where your calculator really can come into play. So grab your calculator right now. And we'll just kind of look at one potential way you could do limits via a table on your calculator. What I'd like you to do is go to y equals and plug this into your calculator. I might even show you something new. I don't know if you know this. I learned this a year or two ago. You know how to get fractions if you have a TID4? So go to y equals, hit alpha, and then y equals, and you get this little option for fractions. And you select the first one, and then you can just type it in as is. So what did we have? We had 3x, I already forgot, minus 2 over 6x plus 12. So you don't have to do it that way. You could just put parentheses around the 3x minus 2 and divide by 6x minus 12. But I think that's kind of cool. So what if we just go to table? Now, one thing you could do is you can just keep hitting the down arrow, and you can see your numbers getting bigger and bigger and bigger. Right? Now, one of the other things is notice how all my answers are fractions. That's because of the way I typed it in, which I don't love right now. So I'm wondering if we can get out of that. Let's see if this will do anything. I can do it. But eventually we're going to start getting to some numbers here. Now, that's a lot, right? Because we're only at 50 some. So what about playing with my table? Go second, window. That's your table set. Oh, no, I didn't hit second. Second, window. And that's your table setup. Now, instead of starting at 53, oh, I wanted to go to negative infinity. What if I go to negative 1200. I can't hit my 0 button, so I'm just going to go a big number, big negative number. And then instead of going up by ones, what if I wanted to go up by, let's see, what if I wanted to go up by 1,000? Now that I can hit my 0, I'm going to change that to a friendly number. Let's start at 10,000. So I changed the start, I changed the change in the table, and watch what happens. Second table. Now I start getting those decimals to appear. But I want to go more negative direction, so I'm actually going to hit up. I forgot we were going to negative infinity. And you can see I'm going up by 1,000 each time. Well, look at my answer. Is it changing? The output is staying the same. It's getting closer and closer to a special number, which means the closer I get here, this answer is going to get closer and closer to 0.5. So if I keep going, and if I reach negative infinity, which you never can do, my answer is going to get closer and closer to 0.5. So that's one way to evaluate this, to get positive 0.5. You can just scroll on your table. It's kind of annoying, right? So isn't there a faster way? Is there a better way to think of this? And we're going to use this idea of substitution pretty loosely right now. But what if I take the limit as x goes to negative infinity of, now instead of f of x here, you know what f of x is equal to. So I'm actually going to plug that in. So here's what we're going to do. Since x is approaching negative infinity, and I have two spots where there's going to be an x, what if I just plugged in negative infinity? Now you have to think conceptually here to do this. I don't know officially what 3 times negative infinity is, but if I triple negative infinity, what do I get? What do you think? 3 times negative infinity is still negative infinity, right? It's the farthest we can possibly imagine, but 3 times further. So what if I do this whole thing right here ends up being negative infinity? What if I subtract 2 from that? Is that going to matter? So the top part is going to reach negative infinity, but it's going to have 3 times that value. And we'll talk about that in a second. But the bottom is going to be 6 times negative infinity. Do you think that adding 12 is really going to matter? No. So the extra little pieces here really don't matter. And then I have a negative infinity over a negative infinity. Those are basically going to reduce out. And what's left over is the fact that the top is a function of 3 and the bottom is a function of 6. Well, that reduces down to 1/2. And notice my table here. Where were the answers headed? It showed me it was 1/2. Now there's a much better way, a friendlier way to do this without doing all this substitution. It's called the end behavior model. And look at this. Because we're going to negative infinity, that -2 isn't going to matter. Right? And that 12 isn't going to matter in the long run. What matters is the 3 and 6. And what if I gave you just this as an expression? 3x over 6x. Do the x's matter? They're going to reduce out. And what's left over is 3 over 6 or 1/2. Which is exactly what our table is showing. So there's a couple different ways to think of it. Does this look like via a graph? So let me show you Desmos really quick. And I just graphed the function here. Let's analyze this graph. If you remember something from, I just actually am currently teaching this in Algebra 2. This is a rational function. It's a fraction with polynomials in the numerator and denominator. That's where we have some vertical and horizontal asymptotes that appear. The key word right there for us is horizontal asymptote. So let's look at this. If I zoom way, way out, does the middle of this graph really matter? Not really. What if I follow a point on this line? Look at the outputs here. So if I'm at negative 100.2 or 103, my y value is close to 0.5. And the further I get out, the closer it's getting to that 0.5. And if I keep zooming out, now that doesn't do it justice. See how my y value is hitting that 0.5? I could keep going out and out and out. And eventually, it's going to just get so close that the y value is going to say, hey, it's 0.5. You're going to approach it. We actually will never hit that because it's an asymptote. But a quick refresher here. As x approaches negative infinity, which means my x values go further to the left, I will approach 1/2. What about if I go to the right? What if I approach x from the right-hand side? What's your y value? Where do you think your y values are headed? Zoom out even more. Still approaching 0.5, except where they're doing it from the bottom side instead of the top side. So these numbers are less than 0.5, whereas these numbers are greater than 0.5. And if you remember anything about rational functions, that's the definition of an asymptote. So, quick little sketch of our graph. We're not going to do this with great detail, but I'd like you to draw this in. If I told you to create that graph, you know that it's going to look like that. And we also know that we have that horizontal asymptote at y equals 0.5. So as x goes to negative infinity, that's really, really far left. We know that this graph is going to get closer and closer to the line of y equals 0.5, which is why the limit is 0.5. Same thing as if I went to positive infinity. If we have a graph, graphs are really friendly to read. This is telling me as x goes to positive infinity, so as my numbers get bigger and bigger and bigger, where's this graph going to head? It's going to hit that same asymptote at 0.5. Now, I just showed you 3 different ways for the same problem. If you have the graph, that's the easiest, because you can just read the graph like we did before. You just have to remember that this arrow reads as x approaches negative infinity. So I'm going to the far, far left of my graph. This one is as x approaches positive infinity, far, far left. And you just read where the graph is headed. Okay, so what if I have a different kind of function? Now, the table, we're just going to do this in our calculator. You don't have to write the table side down. But let's use our calculator to figure out where is the limit going to be as x approaches positive infinity. So I go to the far, far right of the graph, or I go really high in x values. Where's this answer going to be? And you might even know just by looking at the function. But go ahead and hit y equals. I don't think I'm going to do that fraction piece that I showed you because I don't want my answers to be fraction. I want my answers to be decimals. But go to y equals, just plug it in. All right, so let me show you what I did. I just plugged it in. Top function divided by the bottom. And then I'm going to go to table. However, my table's really messed up right now because of the way I had the table set. So I'm going to go second window. And I don't want it to start really low. I might want to start high because I want to go towards positive infinity. If you want, you can put 0 though. I'm having a lot of issues today with technology. So maybe I just want to start at 0 and I want it to go up by 1,000. Then I'll go second table. So you can see here's 0, and now I'm just going to keep growing. Right? So where am I headed to as I keep growing? I'm getting pretty big in my x values. Do you notice a pattern at all? Are we approaching the same number? Are these y values the same? Yeah, they're growing, right? But they're not all approaching. On the last example, they were approaching, all were getting close to 0.5. Well, in this case, it looks like I'm getting pretty big here in my y values. It looks like my y value is the same as my x value, right? So if the y is the same as the x, and x is going to keep growing, that means y is going to keep growing. Which tells me that this table, if I go to infinity in x, that means y is equal to infinity as well. And we have two ways to write this, right? It's actually going to positive infinity. But as we've learned, positive infinity actually doesn't exist. It's a concept, so I'll never ever reach that number because it keeps on growing. So you might see the answer does not exist, or you might see the answer as positive infinity, and either one of those is acceptable. So let's think about substitution right now. What if I just plugged in x equals infinity? Right? I plug it into the original equation. Well, let's think of this. If I have infinity minus 2 times infinity plus 3 over infinity plus 1, do all those pluses and minuses of 2 and 3, does that matter? No, it's like LeBron James losing $1. Right? It's not going to change anything. So what's really happening is I have infinity on top over infinity times infinity on top over infinity on the bottom. Well, I've got actually increasing at a higher rate at the top. And this isn't 100% mathematically accurate, but what's happening is you have one more infinity left over on top, which means my function is growing, growing, growing. So the top numerator is outgrowing the bottom, which means my answer is going to be forever increasing. So, what does this look like on the graph? Because we want to make that connection to a graph. So I'm just going to quickly throw it in Desmos because it's friendly. And let's just confirm that, you know what, my graph looks the same. Now, this is kind of an interesting function too. But here's the graph. So let's think of this. As I go to the far, far right, where's my function headed? Well, the red line is going up. So as I zoom out, notice how that red function is always going up. It's always increasing. As I keep zooming out and out and out, it almost looks like a linear equation when you go far enough. But we are forever increasing as x gets bigger and bigger, which is confirmation that we're going to infinity. Okay. Now, there's one other thing that you could do with this problem. It's really the x values that control it. Watch what happens. If I was to FOIL this whole thing out, right? X times x, x minus x plus 3 minus 2x minus 6, I would get this over this. Well, as we learned, if you look at the very ends of the graph, all this extra stuff right here and here, it's not going to affect the answer as x is really big. The only thing that affects the answer are the two items out in front. Well, wait a minute. Do I have more x's on top or on bottom? More on top. Which if I reduce in x, I end up with x over 1. And if x is going to infinity, and I plug infinity in, isn't that just infinity over 1? Which shows the growth. So you don't have to worry about that. All right, I want you guys to think about this one. Try this one. Your goal is to determine what is the limit of this function as x goes to infinity. And you have 3 different ways you can think about it. With a graph, substitution, or a table. Let's have you figure it out, and then we'll go over it in just a minute. So we'll explore a table first. Type the function into y equals. I'm going to just make sure my table set is accurate. Let's just say I want it to start at 1. And then I'm going to be going to positive infinity, so I want my table to grow quickly, so I have a large change in the table. And once I have that set, I'll go second table. And look at the answers here. Right? My y values are growing very quickly. Actually, I take that back. Scientific notation. Notice how it's a negative? So you also have to know how to read your calculator. You should be able to look at this and see this is 1.33 e to the negative 6. That's like saying it's the scientific notation, and this decimal is moving 6 spots to the left because it's negative, which that number is very, very small. And as I go larger in the x values, so as my x values start to grow, look at my outputs. My outputs are having more exponents that are negative, so now I'm moving this 9 decimal spots to the right. What answer am I eventually getting towards? Well, if we keep growing and growing and growing, we're going to keep adding decimals or decimal spots. So the number isn't ever going to turn negative, but it's going to get closer and closer to basically being 0. So this is kind of tricky. If you use your calculator, you have to know how to read your table. And if I just pick, to show what, we're teaching more than just limits right here. But if I have 1.2, 2, and so on, e to the negative 10, or negative 9, that's another way to write it. And then I'm going to make this jump 1, 2, 3, 4, 5, 6, 7, 8, 9. That number is basically 0. It's so small that you're going to hit 0. So, my answer is 0. Now, substitution, that's kind of annoying, right? Plugging it in. You have to be very careful with positives here. But what I'd show you, and what we'll hint at a little bit, but this will be more next week, if you go to positive or negative infinity, the extra stuff isn't going to matter in the problem. It's going to be reduced out, and all we're looking at is what's called the end behavior model. Well, notice I've got x squared on top and x to the 4th on bottom. If I just looked at that, I would have 4/3 x squared. Right? Because this squared will reduce out. And now, what if I plug infinity in for that reduced version? Well, infinity squared times 3 is still infinity. If I took 4 divided by infinity, my calculus students always kind of struggle with this. If I have a rope that's 4 units long, 4 feet long, and I divide it into an infinite amount of slices, how big is one of those slices? Infinite amount of pieces, it's so small that it's basically 0. And that's where the 0 officially comes from. Okay. So I'm just kind of helping your frame of mind there. All right, and then last thing, we'll look at the zoom graph. No, right? If it's 200, if you took a rope that's 200 feet and you divide it into an infinite amount of pieces, it's still super small, right? What if it's 10 billion? Still divide it up into an infinite amount of pieces. So I like to think of it that way. And again, next week we're going to focus a lot on that. But let me show you just this last piece. Uncover that. So I'm just typing this into Desmos. I'll share it with you in just a second. Okay. So here's my graph. If we zoom in carefully, it looks like a pretty unique graph, right? In the middle. But we don't care about when x is 1 or x is 2. We care about when x is positive infinity. So what happens is I go to the far right. You can see your y values are getting very, very small, but they'll never turn negative. So they're going to go right into 0. So via a graph, it's that same answer. So 3 ways to think of it. Table, graph, substitution. You might not be comfortable with substitution right now. If you can get it from a graph or a table, you're in the right spot. All right, delta math tonight, we'll have you focus on that. Tables with delta math are really friendly, right? They showed us that. The last one, you can just type in an extra 0 at the end of a point, and it'll keep generating that output. So delta math makes the table part really quick. All right, that's all I have. Remember, you got a quiz on Friday.